now that we've seen what the three main elementary operations are, I wanted to do an example where I explicitly use some of these, and then we can see kind of the method here when solving a system of equations. So let's consider and I think for the sake of space, I'm going to use smaller font. Let's say we have the system of equations x plus 3y plus 6z equals 25. We have 2x plus 7y plus 14z equals 58. And then we have 2y plus 5z equals 19. And we want to use elementary operations to find a solution to this, if it exists, right? We know that there is no guarantee of a solution for any given system of equations. So what I'm going to do here is we have this system, and I'm going to kind of group each step here. So here is the system I'm starting with, and we know this third elementary operation that I was discussing was that you can add a multiple of one of these equations to another. And so what I want to do here is I'm going to replace equation 2. So here, I'm going to take equation 2, and I'm going to replace it with -2 times equation 1 plus equation 2, right? We're adding equation 1 by a multiple of -2 to the equation that we want to replace, which is E2. And so let's see what our system would become under this change here. And so now, well, equation 1 and equation 3 are not changing, right? So we could just go ahead and say x plus 3y plus 6z equals 25. That stays the same. And then we have the third equation is 2y plus 5z equals 19. This equation 3 is unchanged as well. Then what did we do with equation 2? Well, we're taking -2 times equation 1, which would be, let me color code what I'm doing here. First, we take equation 2 times, or excuse me, equation 1 times -2. That's -2x minus 6y minus 12z equals 50, right? And then so we're taking that and we're adding it to the second equation. So if we do that, and sorry here, I'm going to write equals 50. Please excuse the bad board work. And then we're adding equation 2. So we have 2x plus 7y plus 14z equals 58, right? And we're adding these. When we add -2x to x, right, basically we're combining like terms. We have -2x plus 2x, well, that's 0. Then we have -6y plus 7y, that's just 1y. And then we have -12 plus 14, that's plus 2z equals, and then we have, this should be, pardon me, it should be a -50. And so we have -50 plus 58, well, that gives us 8. And so now the equation that we're replacing equation 2 with is y plus 2z equals 8. And these systems are equivalent. What we could do next is, because what are we trying to do, right? Maybe I'll stop for a second. We're trying to solve for x, y, and z such that all of these equations are true. Well, and to do that, you need to solve for one first, right? You can't solve for all of them at once. You need to methodically try and find a value or solution for just one variable first. And so what we've done here in replacing equation 2 with -2 times equation 1 plus equation 2 is really we've eliminated x from that second equation in this system, right? And so now we can use that to our advantage and do something similar to get rid of, say, like y or z, and then we'll just be left with one variable, and then we can solve explicitly for that solution insofar as it exists. And so what I want to do in the next step here is I'm going to take equation 3 and I'm going to replace it with -2 times equation 2 plus equation 3. And so let's see what we get here. And then just for the sake of convenience, I'll copy this again. So we have x plus 3y plus 6z equals 25. We simplified this to y plus 2z equals 8. And then we had 2y plus 5z equals 19. And so now when we take equation 3 and replace it with -2 times equation 2 plus equation 3, let's see what we get, right? And again, we picked this number because if we multiply y up here by -2, well, then we can get, once we add these equations, we can get that variable to disappear, right? And so what we'll get is equation 1 stayed the same. Equation 2 stayed the same. And then equation 3 is now replaced with, well, we'll take -2 times equation 2. This is -2y minus 4z equals -16. And then we're adding equation 3, which is 2y plus 5z equals 19. This sum is going to give us z equals 3. And so via 2 elementary operations, we've learned that z equals 3. And then we do what's called back substituting. So here, we're going to do back substitution. And basically what this is we take z equals 3 and we sub this backwards, right? We started with these equations and then we made all these simplifications to remove variables. And now we go back and say, well, okay, we have to find what that variable was, right? And so now we're going back and we knew that y plus 2z equals 8, right? From equation 2. Well, when z equals 3, this tells us that y is 2. And then we back sub one more time. And so now we have z equals 3 and y equals 2. We can use this to back sub into equation 1. So we have x plus 3y, and so that's 3 times 2 is 6, and then plus 6z, so that's 6 times 3 is 18 equals 25. And it looks like 24 minus 25, this gets us x equals 1. And so the solution, there's a unique solution of xyz equals 1, 2, 3. So this is an example of solving a system of equations using elementary row operations. And I want to use this example to emphasize my points about how methods of solving are not unique. And you can do this in kind of whatever way you are the best at, or if you find something that would be the fastest, that's fine. So I'll just provide an alternate method for just to kind of show that you don't have to do it exactly how I've done if you think you can solve it in a way that's better for you differently. So let's rewrite our system here. equals 58. And then we had 2y plus 5z equals 19. One example or one method here, which is something that kind of catches my eye, is we can take equation 1 and solve for x. If we take equation 1, we can rewrite that as x equals 25 minus 3y minus 6z. And then we use this substitution now. Well, anywhere we see an x in the other equations, we can replace that x now as a function of y and z. And so equation, if you would like to keep track of like where we're at with our system, we've rewritten equation 1, right? And now we're going to substitute x in as 25 minus 3y minus 6z. So we're going to have 2 times x. So that's going to be 2 times 25 minus 3y minus 6z plus 7y plus 14z equals 58. And then equation 3 has not changed. Right. And so now let's simplify equation 2 there. And if we do that, we end up getting, well, let's see. We have 50. And then, so let's just write it out. Let's be explicit. We have 50, minus 6y minus 12z. And then it was plus 7y plus 14z equals 58. And then we also had x equals 25 minus 3y minus 6z. That was equation 1. And then equation 3 was 2y plus 5z equals 19, right? And then equation 2 here simplifies even more. You can see we subtract the 50 over, and then we have 58 minus 50. Well, that's just 8. And then we have negative 6y plus 7y. So that would just become 1. And then with z, we see we have 2z. So again, we end up with y plus 2z equals 8. And now we can do the same thing. I notice that how in equation 1 I could solve for x. Well, now in equation 2, I can solve for y, right? So I can rewrite equation 2 as y equals 8 minus 2z. Then we substitute, just like we did with x. And you'll notice here that we get, and I'll kind of just do this in one step here. So we're getting 16 minus 4z plus 5z equals 19, which again, we see z equals 3 right away, right? And then we back substitute again. So if z equals 3, then y equals 8 minus 6, which is 2. And then if you plug everything in, right, you take z equals 3, plug it in here, y equals 2, plug it in there, you're going to get 25 minus 24. And again, you'll get x equals 1, right? So here's an alternate method purely based on substitution. And we didn't really use any elementary operations here, right? So there are other ways to solving these systems. And aside from preference, sometimes you can determine which method to use based on convenience, right? If you have like a variable already solved for, well, then substitution may be more fast, right? It may be something quicker. So you can always just kind of gauge which method you want to use from problem to problem. And I want to finish this video with a few definitions, basically just to have a sufficient vocabulary here. So let's look at definitions. really quickly. So if we have a system of equations, we were looking at like this. Let's say we have the following system, like A11, X1 plus et cetera, A sub 1 n xn equals B1, and this went all the way down to like A sub n1 x1 plus A sub m n xn equals B sub m, right? This is an m by n system, meaning there are m equations and n variables. We say if B1 equals B2 equals B sub m equals 0. So basically we just have on the right-hand side there, all these equations are equal to 0. We say the system is homogeneous. And we'll explore these in more detail later, but for now, it's important that we understand what a homogeneous system is. And it's basically when every equation is equal to 0. If we have so here's another definition. If the set of points, we'll use these brackets represent set notation here. If the set of points x, y, z, or however many variables, let's say like if we're still looking at an m by n, and then let's say x1 up through xn, if this set of points is a collection of solutions to the system, then we simply say, so let's see, if this set of points solves the system, we say it is the solution set. Maybe a trivial definition, but we will refer to solution sets in more detail in the future. 2 more definitions, and then I think we will call it a video. If a solution exists, and I mean at least one, if infinitely many solutions exist, well then a solution exists, we say the system is consistent. And if no solutions exist, we say the system is inconsistent. Fittingly. Okay, so I wanted to include this kind of a detailed example and these definitions here so that we are more well-rounded and well-equipped to starting to apply these things in the near future. So again, in part 2, we will talk about solving these systems via matrix representation.